guys, a warm welcome to you. Now I have come up with a new part, that is Curie's law and hysteresis in magnetism. Here we will going to study that how the material changes as we keep on changing the temperature, and moreover we have to see that how can we magnetize and demagnetize a particular material. So this is what we have to see in this part. So for this detailed discussion, let's proceed. So guys, Curie's law and hysteresis. Now let's look first that what does Curie's law states. Now, as the temperature is increased, the randomization of individual atomic magnetic moment increases. Okay, what do we know? The magnetic moment is in the atoms is only because of the movement of the electrons. So what does this Curie's law states that as the temperature is increased, the randomization of the individual atomic magnetic moment increases, so decreasing the magnetization I for a given magnetic intensity H. So whatever you apply the magnetic intensity H, accordingly your magnetization decreases. So the resultant magnetic field decreases, which means this X is actually the susceptibility, where you have studied in the previous part as Cm. So this is susceptibility decreases as temperature increases. Now Curie's law states that far away from the saturation, the susceptibility of a paramagnetic substance, this should be kept in mind that this is paramagnetic substance, is inversely proportional to the absolute temperature, whichever absolute temperature you apply. So therefore the susceptibility is C by T, where C is the constant, or you call it as the Curie constant. This is the formula which you are supposed to remember, that susceptibility is inversely proportional to the absolute temperature. Now let's proceed. Now what after that, when a ferromagnetic material is heated, so what happens, it becomes paramagnetic at a certain temperature, and this temperature is called Curie point or a Curie temperature. So therefore after the susceptibility varies with temperature as this formula, C dash upon T minus Tc, where Tc is the Curie point, means whatever is the temperature at that Curie point. So therefore where Tc is the Curie point and C is the Curie point of, so C dash is the constant. So the Curie point of iron is 1043. So it's a very large value, 1043 Kelvin. Now come to the hysteresis loop. Now what is a hysteresis loop, or we call it as the magnetization curve. So what is a hysteresis loop? Hysteresis loop, it is the curve which shows the variation between the magnetization or the intensity of magnetization in the material with respect to the applying magnetic field, or with respect to applying magnetic force H. So therefore it is the curve between I and H. So what do we have? So what do we take from this thing is that the intensity of magnetization I increases with increase in the magnetizing force. That means whatever force you are, or whatever field you are applying across the material, so what you are seeing, the intensity of magnetization is increasing, and it increases through this point starting from O, because initially everything was 0, so it starts from O and goes to point A, something like this, and reaches the saturation at point A. Now this is the saturated value. Okay, now what else? When the H is decreased after saturation, now what we want? Well, now we are decreasing the value of H. I decreases, but it does not come to 0 at H equals to 0. This you can see that on decreasing the value of H, it does not follow this path, it follows this path, and it stops over here, means it does not stop over here. That means what we can see is that the magnetization remains over here when we decrease, or when we take the H equals to 0. That means at H equals to 0, it still have the magnetization. So therefore what we have, the residual magnetism So what we have, the residual magnetism set up in the material is represented by OB, and this is called the retentivity. So let's look at the graph once again. OB, this is called the residual magnetism, or this is called the retentivity. R. Now let's proceed. To bring I to 0, that means to demagnetize completely. Demagnetization means that we are applying the field in the opposite direction, or we are reversing the direction of the field. So our opposite magnetizing force is applied. This magnetizing force represented by OC, and this is called the coercivity. That means when the magnetism inside the material goes to 0, what is the value of H? You call, or you represent this by OC, or coercivity. This is your coercivity. C. Let us represent it by C. So therefore, after reaching the saturation D, now after reaching the saturation level D, when the magnetizing force is reversed, the curve closes to point A, completing a cycle, something like this. So when it reaches to saturation, after that, now again we are reversing the direction of H. So therefore, what we are going to get? It goes something like this and reaches to A by completing the curve. This is what exactly is your hysteresis loop. Okay. So therefore the loop A B C D E F A is the hysteresis loop, and the area of the loop gives the loss of energy due to the cycle of magnetization and demagnetization, and is dissipated in the form of heat. So this should be kept in mind. The area of the loop gives the loss of energy. This should be kept in mind. This is very important thing. Now let's proceed. So what we have next is that material like iron having thin loop is used for making temporary magnets, and that with thick loop is like steel is used for making permanent magnet. Okay, so this thing we'll do it in the details just after this thing. That means in a brief thing, why it is so, why do we need thick loop for making permanent magnet? Because what do we want? That it should not magnetize or demagnetize easily by applying the field. Whatever field you are applying, it should not magnetize or demagnetize easily. So therefore it should have a very high value of retentivity or coercivity. So therefore that means why thick loop? So we have studied about this thing. Thick loop means energy loss is more. That means if energy loss is more, that means very high amount of energy is required to magnetize or demagnetize the permanent magnet. So this is what we need. So this is what exactly, why do we need thick loop for permanent magnet and thin loop for temporary magnet. Now let's proceed. So here is the comparison between a soft iron and a steel. So therefore figure shows the hysteresis loop. This figure and this figure shows the hysteresis loop for soft iron and a steel. So therefore you have studied about this thing here. You have studied about this thing that okay, this is written over here also, that this is for steel and this is for soft iron. Otherwise I was asked about this thing from your side, that what is for thick loop is for steel or whether thin loop is for steel. So it is written over here. Steel is for thick loop because it is helpful in making the permanent magnet. This we have studied. Now the retentivity and the coercive force are larger for steel than for soft iron. So this we can see it from the figure, that the retentivity and coercive force are larger. So this we can see it from the figure. This value and this value are larger for the thicker one as compared to thinner one. Now, so therefore the area of the hysteresis loop is also larger for steel than for soft iron. So soft iron is therefore easily magnetized by magnetizing field. So also I have told you that it is easily magnetized, means you can easily magnetize this thing by applying the field because of its thin loop, or it can be easily magnetized or demagnetized. But only a small magnetization is retained when field is removed. So also the loss of energy as the material is taken through periodic variations in magnetizing field is small. So we have already talked about this thing that that the loss of energy is means loss of energy is less for this thing, and the materials like soft iron. So these were the properties, means these were the certain things or characteristics of the soft iron which we are doing, and simultaneously I am telling you that why soft iron is for temporary magnet and steel is for permanent magnet. So like materials like soft iron are suitable for making electromagnets cores inside the current carrying to increase the magnetic field easily, because what do we need? We only need that magnetic field should increase. So therefore in transformer also, moving coil, galvanometer, etc., soft iron core is used in the coils just to increase the magnetic intensity. Means you are increasing, you must have done in your transformer, the field line goes something like this. Okay. On the other hand, the steel and the similar materials are suitable for making permanent materials, are suitable for making permanent magnets. Okay, this is something. Okay, are used suitable for making permanent magnets, steel and similar materials. So large magnetizing, why it is so, large magnetizing field is required to magnetize the material. So this is the reason why they are used for making the permanent magnet. But once magnetized, the magnetization is retained to a large extent even when the magnetizing field is removed. This is called your retentivity is very large. That means you need very high value of magnetic field to demagnetize it completely. So, and this is what exactly are called the coercivity. So magnetization is not easily destroyed if the material is exposed to stray reverse field. That is called the coercive force is very large. So this is what we need in the permanent magnet, that it should produce its own field. It should not be something like that when we put it in other field it should magnetize or demagnetize easily. This is what we don't need this is what we don't want in the permanent magnet. Now let's proceed towards the example. So for a substance BH hysteresis curve are given in the figure. For making temporary magnet, which of the following is the best? So what we have studied just now, that for making temporary magnet, what do we need? We need that loop which is very, or what do we need? In comparison, we need thin loop, and such that the retentivity and coercivity should be very small for making temporary magnet. So according to this, if we compare the four options, option number D should be correct. Only this option shows that this has a very thin loop. Now let's proceed towards the next example. So the variation of magnetic susceptibility chi with absolute temperature for a ferromagnetic material. Now what do we see for a, so you must have seen that for a paramagnetic the susceptibility is equals to inversely proportional to T. But what you have seen that the susceptibility for the ferromagnetic is C dash upon T minus Tc, where Tc was your Curie point. After this point, the ferromagnetic material behaves as a paramagnetic. That means if we look at the characteristics of a paramagnetic, the characteristics of paramagnetic are something like this. That means it should follow this ferromagnetic material should follow this curve after certain Curie temperature. This is what exactly it means. So therefore if we look at this option, if we look at option number C, option number D, we can directly neglect this thing. The thing left is option number A and option number B, that from where we have to choose. That means this shows, option number B shows the paramagnetic characteristics. That means this should also be neglected. So option A is left. That means which exactly explains that material has some characteristics, but after Curie temperature it becomes paramagnetic. So it has its, let's say it has its Curie temperature or a Curie point over here, and after that it is becoming paramagnetic. So according to this, option A should be correct.
Hopefully guys, you understood that what we have done in this part. So we have seen that how the material changes with temperature, how the behavior actually changes with the temperature, and moreover how the curve changes upon magnetization and demagnetization. So up till now, all the parts are over, means we have formulated the theory. Now what we are supposed to do, we are supposed to apply this theory in the questions. So next time I'll come up with a new part, that is the previous year JEE questions. So for that, stay tuned.